This is a demonstration to support Grand Rapids Community College BA 254 White Paper 7.1, applying the central limit theorem. There's a ton of information out there on the central limit theorem and the importance of the central limit theorem within statistics and mathematics and in general. The intent of this white paper is to assume that that information's already been communicated. There's some great resources that are out there everywhere. So instead, this is going to focus on the specific application of the central limit theorem, and specifically providing a z-distribution, or I should say a z-value, and assuming normality, but a z-value that relates to a population sample. To do this, we're going to go through problem number 1 from White Paper 7.1. It says, recently a professor went on a tour through one of the many local breweries. The professor stepped into the quality control office to talk to some of the employees, struck up a conversation with a few of the employees, and found out one of the things they were checking was the operation of the bottle filling line. At the start of their shift, one of the employees randomly selected 36 bottles from the filling line. He found that the average volume within the sample, or the average from the 36, was 12.10 ounces. The employees know that the equipment was set up to run a population mean of 12.05 ounces and a standard deviation of 0.12 ounces. Then it asks a very generic question, or a general question as well. Does it appear as though the brewery is overfilling the bottles, or should they just continue to operate with their current settings for the rest of the shift? In terms of the mechanics in solving this problem, the first thing I would encourage you to do, and the first thing we're going to do now, is to write out the given information in the problem. So given to us in the problem was a sample size of 36. From that 36, the sample mean was 12.10 ounces. Additionally, and this is a pretty expansive thing to be able to say, but we know that the population mean should be at 12.05 ounces and the population standard deviation of 0.12. Now again, statisticians can argue about this. But what I've said in the past in an example like this is when the people put together this filling line, they knew what to expect. There's a long process of making sure that this equipment is manufactured to a certain standard and is operating to that standard. And these people that are running this bottle line, filling line, have been doing this for a while. They understand what the equipment is doing. And so when we say that these values are known, while unusual in some cases, it's not a stretch in this one. Additionally, we can calculate another piece of given information. We could say our sampling error, which is simply what the difference between our sample and our population value. Our sampling error here in this case is 0.05 ounces, which again, to be blunt, doesn't seem like a lot. But what we're trying to figure out in this case is, statistically speaking, is this value and then correspondingly this value, are they unexpected? Is this, statistically speaking, this sample quite a ways away from where we believe that it should be? In this case, it should be at 12.05. To start to kind of map out this problem, it's not explicitly stated here, but our sample size now, our sample size is greater than or equal to 30. We're going to assume now a z-distribution. There will be more on that later when we talk about when we don't know what this population value is, or we don't have a sample size that's large and representative of the entire population. But in this case, our standard is going to be, we're going to employ a z-distribution. The distribution of these values are going to be normal. We know that this normal distribution is centered here at 12.05. Our question is, statistically speaking, the sample value of 12.10, is this a long ways away statistically speaking, or is it fairly close? We would expect our sample value to be very close to here, which would result in a very low sample error. All right. To do this, what we're going to do is then go in and tap back into some familiar territory. We're going to calculate a z-value. But now we're going to employ the central limit theorem, and we're going to calculate this z-value by looking at a sample mean. So we're going to take our sample mean minus our population mean divided by the standard deviation over the square root of n. We plug in these values to get this z-value, our x bar of 12.10 minus 12.05 divided by my standard deviation, which was 0.12 over the square root of 36. If we run this calculation, we end up with a z-value of positive 2.50. So our value of z, our standard normal value that lines up to our sample now is 2.05. We can then use this z-value as a way to find out what this area is in our normal distribution. If we look at our z-distribution chart, what we find is that this area in our normal distribution is 0.4938, and then correspondingly the area left over here is 0.0062. Again, we can get the 0.0062 by just simply saying we have half of our distribution on this side of our population mean, and of course if we were working on the other side of the distribution, the same thing is true, because remember, these normal distributions are symmetrical about the mean. Basically, what this tells us when we look at these specific numbers is there's basically a less than 1% chance that we're filling the bottles appropriately. In that, statistically speaking, we would not expect to see this 2.10 ounces. And even more bluntly, if we were operating this particular line, what we would say is we would use this data to go out and make some type of adjustment to the line, because clearly we are kind of, in this case, overfilling these bottles, which in practical terms as well becomes an issue when you're dealing with a large volume operation. So there is a definite business connotation here in that if we're looking, even though these are small increments in a large volume, these small increments can become very large numbers. All right. This has been the video demonstration for, again, White Paper 7.1 at Grand Rapids Community College.